starting a new unit today. We are starting a unit on functions. I'm going to record it because I do not think the video that I have on Moodle uploaded properly. So we are moving on from what we had our test on before fall break, simply because we need to move on for time's sake. I do still have the different tests. It's something we're going to look at later, but we're going to move on today. I just heard y'all might be out September 29th to practice SAT or something like that. October, I'm sorry, yeah, you're right. So we're going to move on, and we're going to start with our functions note. So what we're going to do right now is we're just going to copy down the notes up to this point where it says graphing quadratic equations. So, up to that point in time, we're just going to copy down the rules today. Okay, this top part, this is lesson number 1. And then we will go to our other purple packet and we'll do some practice. If you did not pick up the packet when you came in, it's beside the calculators and you need one of each. So again, right now, we're not trying to get a bunch of understanding. We're trying to copy down the notes. Then we'll go to the other packet where it says picture page and we'll practice. So number 1, domain. A relation is a set of ordered pairs, okay? A combination of coordinates. A function is a special ordered pair. Okay, now we'll talk about that down here to determine whether or not it's a function. Does anybody know what the domain is? What is the domain of a relation or a function? Anybody know what domain is? All right, domain are your x values. Well, if your domain are your x values, what do you think range might be? Your y values. So domain are x values and y are range. Y is the range, I should say. Now, I'm going to show you how to keep this straight. D comes before R in the alphabet. Everybody agrees with me on that. Domain alphabetically would come before range alphabetically. And the same thing here, x comes before y alphabetically. So domain goes with x and range goes with y. Now, one thing you need to keep in mind is that this ties over here. The x-axis is the one that goes horizontal, okay? So the x-axis is the horizontal axis. That's your domain. But the y-axis is the one that goes vertical, which is your range. So we have the domain. It's going to be found along your x-axis. And we have your range is going to be found along the y-axis. Now, today's lesson is mostly visual. You're not going to be doing a bunch of algebra. We're not going to be solving a bunch of equations. We're not going to be doing a lot of factoring. We may see a little bit of it, but not much. This is more of a visual lesson. Now, how do you read a book? If you open up a book or you open up an article on your phone or you open up a magazine, how do you read? Left to right. Thank you, Kisan. So we're going to read this from left to right. We're going to read a graph and state its domain from left to right. Now, you do not look at the range the same way. The reason we read a graph from left to right for the domain is because your domain is on your x-axis. It goes from left to right. But your range comes from the y-axis, and so the y-axis is vertical. So we're going to read this from bottom to top. Now, that's very important. You don't get to rotate those and look at it from the top to the bottom. It's always the bottom to the top, the smallest to the largest. I'm going to highlight that because what you're going to see in just a second is that all of the other readings come from left to right. That is the only one that is bottom to top. All right, what are some other words for increasing? We're going to talk about it mathematically, but if somebody says something to you about something increasing, what are some other words that brings to your mind? What? North, okay. What else? Oh, more. I'm sorry. Well, more or north. Good. More. What direction would something be going if it is increasing? Up. Okay, so if something is going up, it's going to be increasing. Now, I thought he said north, but that would have been correct also. Okay, if something's pointing towards the north, it's increasing. If something is pointing towards the south, it would be decreasing. All right, so decreasing means less. It also means going down. Anybody want to add any words there for increasing or decreasing? We're going to talk about it in math. Yes. Okay, so he's saying increasing is going towards the positives. That is true. Decreasing is going to the negatives. That is also true. That's going to play out a little bit differently, so I'm not going to write that down. All right, for increasing and decreasing, we're going to read it from left to right. Again, the only one that is not left to right is that vertical or that range, but everything else is left to right. Now, let me remind you, we're going to copy down the notes, and then we're going to practice, okay? So you don't really even know what I'm talking about yet until we get our practice page. The turning point. Have you ever heard of somebody say, goodness, Sally really had a turning point in her life. She graduated, and she got strung out on drugs, and she just never recovered. You ever heard the word turning point used for a person's life? Okay, if somebody has a turning point in their life, things drastically change. Maybe they were doing really, really good and they started doing really, really bad, or vice versa. They were doing amazing, great things, and then something happened and they just went down the tubes. That's called a turning point. Well, it's the same thing in math. So a turning point occurs at the x coordinate, put that down, not the y. We'll talk about that later when we start practicing. But a turning point occurs at the x coordinate, not the y. And you're going to always use parentheses for increasing and decreasing. We will talk about this in a minute. But for increasing and decreasing, you're always going to use parentheses. And there is a reason why. We'll talk about that in a second. All right, as I said at the beginning, a function is a special relation. A function is a relation in which none of the x's repeat. We're going to talk about that in a little bit more detail later. But there are several ways to denote a function. So you might say f of x. That's one way to say this is a function. You might say g of x. That's another way to say this is a function. H of x. You could have p of x. You can have k of x. But this is function notation. This is just the way to indicate, hey, y'all, this is a function, and this is the way I'm going to write it. All right. A graph is a function. Now, I should say a relation is a function if it passes the VLT. Now, do y'all know what VLT stands for? Very good. That stands for the vertical line test. If a relation passes the vertical line test, then it is a function. If it does not pass the vertical line test, it is not a function. All right, so a relation is a function if it passes the VLT, and the easiest way to look at that is by looking at the graph. So what I want you to do here, we're just going to draw two small graphs over here, and then we're going to draw two small graphs on the right. And we're going to draw some things that are or are not functions. Sketch the graph of something that passes the vertical line test. In other words, when you lay your pencil vertically, sometimes people call it the pencil test. It can only touch the graph one place at a time when you lay your pencil vertically. Okay? Now, there is something called the HLT that we'll get to later. It'll be a while. All right. you can think of the shape of something that does pass the VLT. Let's talk about letters of the alphabet. What is a letter of the alphabet, A through Z, that when I lay my pencil down in all caps, it would never touch that letter of the alphabet more than one time? Nope. Nope. U. Okay, U would work. Now, only if you do it this way. If you make the U curve and come outwards like that, then this would pass the vertical line test. Because there's nowhere that I can lay my pencil on that U that it would cross it more than one point at a time. So this would pass the vertical line test. This is a function because no matter where I put my vertical line, if I put it there, if I put it here, if I put it over here, it's never going to pass, it's never going to touch the vertical line more than one time. Okay? Now, just food for thought, this would be a quadratic equation. Write that down because if you look down just below my squiggly line, that's the next topic is quadratic equations. All right, what is another letter of the alphabet that would pass the vertical line test? It cannot cross the line more than one point at a time. What? V, very good. All right, so let's do a V. Now notice I'm putting arrows on my graphs. This means it goes on forever in both directions. Does anybody know what a V, what type of function is a V when you graph it? We just had a test on this. No, a quadratic makes a U. No, a linear makes a line. I'll give you a hint. It's a mathematical equation that we had on our last test, and it has a V in the spelling of the type of equation. Yes, yes, Shaylee. This is going to be an absolute value graph. Now, we're going to learn that later in this chapter. But I agree. This would pass the vertical line test. It's never going to touch a vertical line. No matter where you lay your vertical line, it's never going to cross the graph more than one place at a time. So this is a function. These are examples of functions because they pass the VLT. Now that's important. Notice that we're on the passes the VLT side. Okay, over to the right, we want to sketch something that fails the VLT. In other words, when I lay my pencil down vertically, it would hit it in more than one place at a time. Let's stick with letters of, let's do shapes. What is a geometric shape that would fail the VLT? Square. All right, what's another one? Circle. So if you take Math 172 next semester, you study circles the entire time. We know that a circle is a mathematical thing. Like circles exist. We can graph circles. We can write equations for circles. It doesn't mean that they're not mathematically sound. All it means is that they're not functions. Because if you lay your pencil down on this circle, it's going to hit the circle 2 times, and that means it fails the VLT. So a circle is a mathematical equation, but it's not a function because it fails the VLT. All right, he said a square. That would also be a good example. A triangle. Those are all good examples. Let's go to letters of the alphabet. What's a letter of the alphabet that would fail the vertical line test? C. Let's do C. That's a good one. All right, so C. If you draw a C, now I'm going to put an arrow on it. This would fail the vertical line test because it crosses the vertical line at 2 places at a time. Now, sometimes it may cross more than twice. 2 is not the limit, but in the examples that we did, it only crossed it twice. All right, there's a little question over here, and let's flesh out the answer to this question. What is the difference between a relation and a function? Okay, now up here I said a relation is a function if it passes the vertical line test. So what cannot repeat in order for a relation to be a function? Is it your x values that can't repeat, or is it your y values that can't repeat? X values, that is correct. All right, so go over here to the side. What is the difference between a relation and a function? A function cannot have any x values, also known as the domain, that repeat. Now, repeat your y values, but you cannot repeat your x values. A function cannot have any x values that repeat. That's what happens when it fails the vertical line test. Then some x value has repeated. All right, so let's practice one of these. Go to your other purple packet. Now keep these notes handy, but we're going to practice on this packet right here. So make sure you've got this to the side, and we're going to look at this called picture page. And we're just going to start with the first one. We won't have time to do all of these, but we're going to do one of them. All right, this paper is a little sloppy. I did make this paper, but I had to use graph paper. It says state the domain and range of each graph, and then tell if the graph is a function and explain why. So let's just start with the domain and the range. All right, remember, let me go back to my sheet. The domain are the x values. That means it's going to be along the horizontal axis, and you read the domain from left to right. So if I go back to my picture, this is my x-axis. I'm looking at this thing horizontally. This is my domain. The ones that go from left to right, that's going to be my domain. Now, it doesn't mean that's where it touches the x-axis. It touches the x-axis at negative, well, that looks like about -1.5, 0, and about 2. That is not what this is talking about. That means if you look at this shape, which I don't even know what this shape is, I made it up. But if you look at this shape from this open circle all the way through to this shooting arrow, what would your x values be? So what you're trying to do is look at it from the left. All right, so let's start from the left. I'm going to do this in red. All right, if you start from the left, you keep approaching, what is the first x value that is going to be used in this particular shape? -2. I agree with him. -2 is the first x value that this graph uses. It doesn't mean it crosses at -2. It means that this point right here is at -2. So my domain is going to be -2. Now, I'm going to come back with parentheses or brackets after I finish my interval. We've already studied interval notation, so we know how to do that. All right, and then I look at my graph to the right, to the right, to the right, to the right. Well, I notice it's got an arrow on it. So what is it doing forever to the right? Yes, infinity. That is good. So my interval is going to be -2, comma, infinity. Excuse me. And then I have to go back based on our first chapter, our first test, and decide if that's going to be parentheses or brackets. So let's look at -2. What kind of circle did I have at -2? Open. So that's going to get a parentheses. And what do we always put with infinity? Parentheses, because we know we cannot contain or capture where infinity ends. So that is the interval for the domain of this graph. All right, let's look at it in terms of range. Let me go back to my paper just to refresh our memory. The range are your y values. Now we know the y-axis is the one that goes vertically. And so we're going to look at this graph from the bottom to the top. So let's look at it. All right, if we're going to go, this is your y, and we're going to go from the bottom of the picture to the top of the picture. Okay, so if we start from the bottom and we come up, 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 what's the first y value that is used in this weird shape? -1. So the first y value is -1. And then we see that it's going up forever. So that's going to be positive infinity because it's going up. That arrow means not only is it going to the right, but it's also going up. So our range starts at -1. Don't put a bracket or parentheses yet. We'll talk about that. It's going to go up to positive infinity. We know that -1 comes before positive infinity. When you write an interval, make sure that the numbers are in order. If you were to reverse those, it would not make sense because infinity does not come before -1. It comes after it. All right, now let's look at -1. Does it look like it actually touched at -1? It does to me. I don't see an open circle. It looks like it went down to -1 and came back up. So we're going to put a bracket at -1, and infinity always gets a parentheses. And then the last question here is this a function, yes or no? And then you have to tell why. That's how it's going to be on the test, yes or no, and why. This is also on the final exam. Go back to your paper. We learned that if it is a function, it has to pass the vertical line test. And if you notice this page, everything on page 8, I gave you a graph for. We can also look at equations, but this is practicing for the graph. So is there anywhere I can lay my vertical line that would hit this shape more than once at the same place? No. So yes, this is a function, circle yes. And the reason is that it passes the VLT. This is a function, and the reason is that it passes the vertical line test. If it were not, you would say it fails the vertical line test. All right, before we go back to the second part of our notes, let's do a couple more on this page. Let's slide up and let's do this thing right here. All right, this is a little bit different. This says tell where the function is increasing or decreasing. We talked about that. Same thing it means in English is what it means in math. If it's increasing, it's going up. If it's decreasing, it's going down. But let's start with the domain and range because that's what we just practiced. Okay, let me refresh your memory. The domain goes along this direction right here. The domain goes from left to right. The domain are your x values. So if we start from the left, what is the first x value that it looks like this thing's going to ever use? -2. So now my domain starts at -2. I'll come back and do my parentheses. And then comma. And then it is shooting to the right forever. What is mathematically to the right? Infinity. So it's going to be -2, comma, infinity. It's looking just like the previous one that we did, actually. It's a different shape, but the domain is the same. And we know we put a parentheses at -2 because it was an open circle, and we always put a parentheses in infinity. There's your domain. You look at the picture from left to right. This is 100% visual today, for the most part, until we get to the next section. And so you have to be able to look at the graph and visualize what is it doing along the x-axis, that's your domain, and then what is it doing along your y-axis, that's your range. All right, now let's look at the range. The range goes along this direction. It's from the bottom to the top. So you just look at the lowest part up to the highest part. So if you start from the bottom and you go up, 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 what's the first y value that this graph starts at? 0. Okay, it starts at 0, and then we see that this goes up and to the right, up and to the right, up and to the right forever. So it's going to be 0 to infinity because it continues to go up. So for your range, put 0, comma, infinity. We know infinity gets a parentheses. And 0 also gets a parentheses because of that open circle. So there's your domain. More pens. All right, you're going to have to listen extremely carefully to this next story. Let me go back to my sheet. On this sheet, we talked about increasing and decreasing. So if a graph is, or if anything's increasing, but we're particularly going to talk about graphs. If a graph is increasing, it's going to be going up. The numbers are going to be getting bigger. If it's decreasing, it's going to be going down. The numbers are going to be getting smaller. Now, this is very important. We read increasing and decreasing from left to right. Remember, the only one that's different is the one that I highlighted. All right, the turning point occurs at the x coordinate, not the y. And you always use parentheses for increasing and decreasing. All right, let's look at this one. So, you ready for my little story? Y'all ready? Keeson, you ready? You ready? Okay. All right, have you ever ridden a roller coaster? Or seen a roller coaster? All right, that's what you need to know to get this correct. So pretend like you're on a roller coaster. Pretend like this is a roller coaster right here. It's not a graph. Pretend like it's a roller coaster at Disney World or the State Fair or County Fair, wherever you go. You always sit your body on the left-hand side of the roller coaster, and you're going to follow its path from left to right. You always go from left to right. And let's just see what our body would be doing if we sat down on this ride right here at this open circle and we rode this ride to the right for all eternity. What would our physical body be doing? Going up, that is correct. And so in math, we call that increasing. So this is increasing. This graph is increasing. It's going up forever. That little arrow indicates that it continues going up and to the right, up and to the right, up and to the right. So this would be like if you got on a ride and it went just to outer space forever and forever and forever. All right, the turning point occurs at the x coordinate, not the y. So let's look at our x. Okay, our x is -2. So from -2 to all infinity, this graph is going to be increasing. It's going to be going up forever. It never falls back down. It never jerks you down. It never comes down the hill. It goes up forever. Now, if you'll go to your notes, I said you always use a parentheses for increasing and decreasing. This is not the best example to explain why, but we're going to put a parentheses here. So from -2 to positive infinity, it increases forever and forever and forever and forever. Now, does the graph ever decrease? No. Don't leave it blank, though. Put none, N-O-N-E, or you can put does not exist. But don't leave it blank, okay, because that makes me think you don't know what's going on. All right, let's try one more. Let's try this one top right. Let's try this one right here. All right, let's start with our domain. Let's try to go in the same order that we did the last one. So our domain, we're looking at this thing from left to right. Okay, this is the direction that we're looking at it. We're looking at it from left to right, and this will be our domain. So now these arrows are important. When you have arrows, that means a lot of things. So what does it look like this thing is doing forever to the left? It's going over, right? Forever to the left. And then it's also going forever to the right, forever to the right. It's kind of like slithering out like this, up and down in both directions, forever and forever and forever. Now, I drew this with my own hand, so it's not amazing. But my domain is going to be negative infinity to positive infinity. Notice that it has arrows going to the left and to the right forever. So this is a continuous function. It never stops. It never has a break. It never has a gap. It goes on forever and forever to the left and to the right. All right, we're going to look at our range. Our range, we know, goes from the bottom to the top. So if we look at this thing, well, what does it look like it's doing from the bottom? Going down for all eternity. What mathematical number is to the bottom, to the bottom, to the bottom, to the bottom? Negative infinity. We know negative infinity gets a parentheses, and then it's shooting up forever to positive infinity. Now, I have people that will put positive infinity first, comma, negative infinity. That is not correct because we have to go in order. You have to put them in order as they come. All right, so that's our domain and range. Now let's talk about our little roller coaster. What side, and I think I said this, but let's see. What side do you sit down on? The left. You always sit down on the left. Good, because you read a graph from left to right. So if we start this thing over here, here's where we sit down because we always sit down on the left. And then we're going to go, whee. What is our body going to do for all eternity? Decrease. Is this a turning point? Is that dot right there a turning point? No. It's decreasing here, and it's decreasing here, and it's decreasing here, and it's decreasing there. It is decreasing for all eternity. You're going to be going down, 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 further and further and further. You're never going to come back up. You're never going to change directions. You're never going to hit a turning point. It's going to go down for all eternity. Well, what is eternity in math? Negative infinity to positive infinity. So negative infinity to positive infinity. And if it is never increasing, put none or put does not exist. But don't leave it blank. Now, I have more of this worksheet worked out for you on Moodle. I'm going to show you that in a few minutes. So we're going to put that worksheet to the side and go back to our notes. That's just a little warm up. All right, there's one more topic I want to cover today, and this is on the notes right here in the middle section, and we're talking about restricting the domain or stating the implied domain. Now, this actually ties along to what we were just talking about. It's not going to feel like it right now. It's going to feel completely disjointed. But as we get to the graphs, this will make more sense. Now, notice I use the word domain twice. So we're going to restrict the domain or we're going to state the implied domain. Just refresh your memory from a couple of minutes ago. The domain are the x values. So we're talking about restricting the x's for a function. Now, let's talk about 0. We've had some issues with this. If 0 is on the top, so I'm going to put a 0 in here, T-O-P. Pretend like you have a 0 on the top of a number, because this ties into your restrictions. So let's say 0 divided by, Keeson, what day of the month is your birthday? Okay, 0 divided by 15. That's 0, right? All right, Johan, what day of the month is your birthday? 18th. That's also 0. All right, Destiny, what's your birthday date? 30. That's also 0. JC, what's your birthday date? That's also 0. So if 0 is on top of a number, it is okay. There's no problem there. The calculator just proved it. What is the answer for all 4 of those people? What's the answer if 0 is on the top? 0. Okay. If 0 is on the top, it is okay. It equals 0. But what about if 0 is in the bottom? We have 2 zeros, and I'm going to tell you what that means. Okay, so let's reverse that. I'll start with myself. My birthday date is 17. So 0 divided by 17. Oh, I'm sorry. It's supposed to be on the bottom. 17 divided by 0. It says error divided by 0. All right, Zamarian, what's your birthday date? 8. 8 divided by 0. Oops, I'm sorry. 8 divided by 0. Nope, it says error divided by 0. Abby, what's your birthday date? 2. Nope. Error divided by 0. So if 0 is in the bottom, it's what I call a no. Now notice you have two O's in the bottom. O here corresponds to no there. O here corresponds to no there. If it is in the bottom, it is a no. It is what the calculator tells us is undefined. It cannot happen. It is undefined. Division by 0 is a no. It is undefined. And we just looked at that using our calculator. Now, based on that, we've gotten one of our restrictions. One of our restrictions for X, we just determined. What did we just say you could not have in the bottom? 0. That's the first restriction. So number 1, no 0 in the denominator. Now, where's the denominator? Bottom. So you cannot ever have a 0 in the bottom of a number. If it is in the denominator, it is undefined. It is a no to have 0 in the bottom. That's your first restriction. Now, you don't have to write this on your packet, but let me just write it on a sticky note so we can talk about it. This is a review. All right, what is the square root of 4? 2. All right, what is the square root of, let's say, 25? 5. Okay, so that's okay, right? We can take the square root of those numbers. But what about if I ask you for the square root of -4? What will we have to hop out because we were asked to take the square root of a negative number? What would have to come out here? I. So this would be 2i. All right, what would the square root of -25 be? Negative, and then comes out and gives us 5i. Y'all remember this? We had a test on this. We've had a quiz on this. We've already studied that. So what we're seeing here, based on this pink sticky note, is you cannot have a negative under the square root. Because if you have a negative under the square root, it is an imaginary number. It is a complex number. Does everybody remember that little sticky note? Solace, I'm sorry, you forgot to take your earbuds out. Please forgive me. I didn't notice it 35 minutes ago. Thank you. So that's our second restriction right here, what I just wrote on this pink sticky note. Everybody said they agree with me on this. So we cannot have a negative under the square root. That's restriction number 2. Just write that down on that second line. No negative under the square. Now you can take the cube root, but you can't take the square root of a negative. No negative under the square root, because if you have a square root and your number is negative, we just talked about it, you're going to have to take out an I. And we don't want to do that. Imaginary numbers are fake numbers. They are not real numbers. So we can't deal with those in this particular topic. Now, I'm going to just tell you this, and then we're going to practice it. So, number 1, if it is in the denominator, you set it not equal to 0, and you solve it. Why? Because of restriction number 1. We just said if it's in the denominator, it cannot equal 0. No 0 in the denominator. So, if it's in the bottom, we have to say, no, 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 you cannot equal 0. All right, now this should be, honestly, this should say square root. It should not say radical. It should say square root. If you want to fix that, that'd be good. A radical is, or I should say, a radical can be a square root, but a radical can also be a cube root or a fourth root or a fifth root or a sixth root. It should say square root. If the square root is in the top, you set it greater than or equal to 0 and you solve. But if it's in the bottom, you set it strictly greater than 0 and solve. And the reason is, if it's in the bottom, we know it can't equal 0 because that goes to restriction number 1. So that's why when it's in the bottom, we say, no, 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 you cannot equal 0 down here, but you have to be strictly greater than. Up here, we say, all right, if you want to be 0 in the top, we'll let you do it. It's okay to equal 0 if it's in the top. It is not okay to equal 0 if it's in the bottom. So there's a difference between if the square root's in the top or in the bottom. Now, this is not going to feel like any connection to what we just did with graphs, but once we learn all of our skeleton graphs and all of our shifts and transformations, these two things will be connected. All right, so you're going to keep that paper to the side, and you're going to flip over to page D. So go to your packet, and let's look at page D. Page D. Now, you've got to have those notes right beside you in order to get page D straight. All right, this says state the implied domain or restrict the domain. Now, that word, when you hear the word domain, we know we're talking about the X values, so we're only worried about the X's. We're not restricting the range. We're restricting the domain. And we just learned on our yellow packet that there are two restrictions. I'm not yellow, sorry, purple. I'm going to look at them right here. Number 1, no 0 in the denominator. And then number 2, no negative under the square root. This is your strategy. I've got these written down right here. Again, that should say square root, not radical. I'll add that. It can't be under the square root. It could be a cube root. All right, number 77. Let's look at this problem. Number 1, let's see if I can, well, number 1, or number 2, I've reversed them. No 0 in the denominator. Does number 77 have a denominator? No, there's a 1 down there, but there's nothing in the denominator for number 77. We're just looking at 77. Let's not go past that. So that does not apply. No, the other restriction says that you can't have a negative under the radical. Well, do we have a radical? Yes, we do. So it's the stuff under the radical that we're looking at. It's going to be x minus 1. Now, you go to your sheet, and it says if the square root is in the top. Well, is this in the top? Yes, it is. This is a square root, and it's in the top. So my sheet tells me to set it greater than or equal to 0. Not the entire radical, just the stuff under the radical. So say x minus 1 must be greater than or equal to 0. It is okay for it to equal 0 for number 77 because it's in the numerator. And it's okay to have 0 in the top. We just talked about that. And so when something crosses the equal sign, we are having little algebra mistakes. Stuff like this is messing you up from your pre-calculus. But when a minus 1 crosses the inequality, it becomes a plus 1. So we've got x is greater than or equal to positive 1. And that is the restriction on the domain for number 77. The x's for number 77 have to be greater than or equal to negative 1. Now, I'm just going to show you why. You don't have to write this down. Put your pencils down. Let me just show you why that is the case. Why do my x's have to be greater than negative 1? I'm at positive 1. Isaac, give us a number, preferably an integer, but anything would work. Give me a number that is not greater than or equal to 1.
-2.
Okay, -2. Y'all agree? -2 is down there? Yeah. So why? So if you don't have to write this down, if we use x equals -2, let's see what's going to happen. Well, we'd have the square root of -2 minus 1, which is the square root of -3. Uh-oh. What would we have to hop out of that -3? an I. So we would have an imaginary number. If we have an integer or a rational, irrational, it doesn't matter. Anything less than 1 is going to give us an imaginary number, and we cannot have imaginary numbers, so that's why we have to put a restriction on the x's. All right, let's look at number 79. Now this one's a little bit different, something we had a test on, but that's okay because y'all did really well. Number 79, let's look at our restrictions. Well, I can look at the restrictions right here. They're up here on the paper. Number 1, no negative under the radical. Do you see a radical anywhere in number 79 at all? No, we do not pay attention to that because it doesn't apply to this problem. The second restriction says no 0 in the denominator. Do we have a denominator? Yes, we do. This is in our denominator. So let's go to our sheet and see what to do. If it's in the denominator, you tell it it cannot equal 0. Whatever you are down there, you cannot be 0. So we're going to set this cannot equal 0.
Why do you just say denominator?
Because that's the only restriction. Do you see any restrictions about the numerator? Nope, it's not a restriction.
So just leave it how it is?
Yep, we don't care anything about the top. 3x can be anything it wants to be. It can be positive, it can be negative, it can be rational, it can be irrational. We don't care anything about 3x. Her question is, why aren't we doing anything with the numerator? Because there are no restrictions on the numerator. You know why? Let's go back to our paper. Can you have 0 in the top? All day long. So we don't really care what 3x is. We don't care if it's positive. We don't care if it's negative. We don't care if it's 0. Nobody cares what 3x is. But we do have to restrict the denominator. Now, we've already had a test on this. X squared, you might want to write kind of small, minus x minus 6 cannot equal 0. We have to factor this. This is a quadratic equation. To factor it, we make our t-chart. We multiply 1 times negative 6, which is negative 6. We take our middle number, which is negative 1. We need to multiply here. We need to add there. We've already had actually 2 tests on this. Factoring is crucial. You have to be able to factor, and you have to be able to factor quickly. So not a 5-minute factoring every time you come onto a trinomial. All right, so what will multiply? Let's see. This would be a negative 3 times a positive 2, and this would be a negative 3 plus a 2. Now, solace. I noticed this on your test. When I set up my parentheses, I know I'm going to copy the lead term, so I'm going to set up 1x here and 1x there, and we know that this cannot equal 0. Solace, what are the factors that you plug into your parentheses? Which numbers are the factors? Yes. Now, Solace got sloppy on his test, and he plugged in negative 6 and 1. He had his chart set up correctly. He had his factors correct, but he got sloppy when he set it up, and he accidentally put a negative 6 and a 1. No, my factors are negative 3 and negative 2. I'm running out of room, but there we go. That's how you factor that. We just had a test on this. The last time I saw y'all, we had a test on solving a quadratic equation by factoring. All right, Johan, what do I now do? Yes, thank you, plus 2. Plus, thank you. What do I do with each of my factors? Well, I normally would set them equal to 0, but today they cannot be 0. So I say, all right, 1x minus 3 cannot equal 0. And 1x plus 2 cannot equal 0. And then I solve these by moving this over, and I say, all right, x, you cannot be 3. And then I move this over, and I say, all right, x, you cannot be negative 2. And these are my restrictions on the domain. These are my restrictions, and I'm going to show you why. Right beside there. I'm going to show you, I'm not just making this up and pulling this out of the sky. I'm going to show you mathematically why 3 and negative 2 cannot ever be used for number 79. I did not just feel like, factoring something for the fun of it. That's not what we're doing here. We are saying, based on this equation, based on this function, let's use, these are all functions, f of x, h of x, g of x, s of x, c of x, they're all functions. Based on the function given to me in number 79, there are two numbers in the universe, only two, that cannot be. That's positive 3 and negative 2. Now, put your pencils down. I don't want you to write this down. I want you to pay very close attention. But let's go over here and let's talk about why x cannot be 3. Let's do that one first. Why can x not be 3? You said it can't be 3. Your math said it can't be 3. Your restriction said it can't be 3. But why? Let me show you why. Don't write this down. If I go to my function and I plug in a 3, so we'd have 3 times 3 on the top. On the bottom, I'd have 3 squared minus 3 minus 6. That would give me 9. 3 squared is 9 minus 3 minus 6. That would keep my 9. 9 minus 3 is 6. Uh-oh, what's 6 minus 6? 0. And we learned 15 minutes ago that that is a no-no. You cannot have 0 in the denominator. This would be undefined. So it does not work. And let me show you the same thing for negative 2. So if we plug in negative 2, we'd have 3 times negative 2. Now you got to square this, be careful, and then minus negative 2. And then subtract 6. It's a little bit of sign, so it'd have negative 6. This is going to give me a positive. Oh, what did I do wrong? Minus a minus turned to a positive. Okay, this is going to be a plus 2, and then subtract 6. That's correct. And then I keep going. 4 plus 2 is 6. Uh-oh, what's 6 minus 6? Right here in the denominator. What's 6 subtract 6? 0. And we cannot have 0 in the denominator. It is undefined. So that is why for number 79, there are 2 restrictions. Because if you were to plug them in, this is why x cannot equal negative 2. It's because when you plug it in, you get something that is undefined. All right. Let me